Fuel Labs.
Hi, can you guys hear me? Okay, great. So, whenever my slides get on. We'll wait patiently. Here we go. Okay, so I'm going to talk to you today about induced demand from blockchain resource pricing, which is a particularly nuanced topic, so bear with me as I try to kind of explain it. So a little bit about myself. My name's John. I am one of the co-founders of Fuel Labs, which is the first green lightning bolt over here, and also one of the co-founders of Celestia Labs, which is the purple galaxy-looking thing over here. And this talk is a follow-up somewhat, in some ways, of a talk that I gave last year at ECC called Weighted Solid Resource Pricing that described how in a world where you have a separation of data availability and execution, that there are multiple orthogonal resources that need to be, that we need to take into consideration how to price these correctly. And in the years since I've given this talk, this topic has, apparently turned into all the rage, where various speakers, even today, have given talks talking about the importance of pricing resources in an L2, and how it's not just as simple as the most naive way where you just have some gas and then you're done. There's much more nuance here, so I'm glad that this topic is kind of finally coming to public light, and that researchers are finally starting to look into this. So, well, I mean, this slide is kind of spoiling, but whenever you talk about the price of something, you always have to consider two things, which is, well, what is a price? How do you determine a price? You determine it from two things: supply and demand, right? That's how you price something. So this talk is going to be about supply and demand of these resources and how they affect the price. We'll start with supply, because this is the fun one, and then we'll go to demand towards the end of the talk. Okay, so here's the supply, essentially. And for those of you who've had the misfortune of reading the Ethereum yellow paper, this may look familiar. It's a table of gas costs for various instruction types, right? There's a gas cost of some very fast instruction, or very low, it's 3 gas, right? So there's something like addition or something, right? You have more expensive gas cost, like the gas cost of a storage set is 20,000, right? And if we have a certain amount of gas per block, let's say 1.5 million gas blocks, and this is how much gas each instruction uses, then that gives you a supply of how many instructions you can execute per block. But how were these numbers determined? And this is going to be kind of the interesting topic of this talk. So how are these determined for Ethereum? Well, okay, we go on Ethereum Stack Exchange. This is one of the first answers, actually. If you look at the link here, the share link, it says Ethereum Stack Exchange answer 132. So this is like a long time ago, right? In 2016. And this guy here is saying, well, how are those numbers determined, right? Okay, there's a spreadsheet. I'm going to show the spreadsheet in a second, or at least I'm going to show some of the relevant parts of it, or a snapshot of the spreadsheet. But we'll explain first, how were the numbers in the spreadsheet actually determined? Well, this might surprise you, but essentially what they did is they ran a bunch of benchmarks on one guy's laptop. They just took some guy's laptop and they said, okay, let's just run a whole bunch of instructions through it and actually benchmark, see how long it takes to run these instructions, right? So you have a bunch of additions, then you go through and just run a whole bunch of additions, right? Potentially with some other stuff, and extract how long do these additions take to run. And this seems like a reasonable way of doing it, right? Like you're targeting a particular machine. Let's say someone's a cheap laptop. Back in the day, they said you could run a node on a Raspberry Pi. You're targeting that. It makes sense that you benchmark it and you say, okay, how long does an instruction take to run? That's how much gas we assign to it, right? That's a perfectly sane, reasonable way of doing this. Okay, so what do the numbers look like? These are actually readable from up here, from up there, I guess. So this is what we saw before. You have on the left here these green things, these fast instructions. You see add is like 3 gas over there, right? And what's important is that the leftmost column, other than the names of the instructions, obviously, is the compute time in microseconds. right? As you can see, there's a very close correlation between the time and compute. So say addition is 3, and the gas cost for addition, which is also 3, right? This makes sense. But when you get to this, this red side over here, things start to get a little different. When you get to the cost of, the time that it takes to do a storage load or a storage write, this is on the order of 50 to 200 microseconds, right? But the actual gas costs for these are substantially different, well, for some of them. Storage load, for instance, was 50 gas, so that's a direct correlation. Storage write had some additional things added to it, right? There's additional columns here, namely that there's some history and some state, some bytes, so those had to be accounted for in the pricing, so storage writes were given a 20,000 gas cost. Right, but storage reads work. Storage reads don't actually write anything to the state. There's no permanence in there. So they were just given a 50 gas cost, exactly correlated with the time in microseconds to run this instruction. So far, all of this seems pretty reasonable, right? Okay, so there's some issues. Obviously, otherwise, it wouldn't be the introduction of this talk. So this is a comment in EIP 648 suggested by Buterin back in, I don't know, many years ago. This is pretty old. To enable parallel transaction execution. I think the EIP is EIP 648, easy parallelizability, which coincidentally is exactly something that we just said is a big topic of, a lot of people today and, various researchers and stuff say that parallel transaction execution and parallelizing the execution and verification of transactions is very important for unlocking maximum performance for rollups going forward. So this guy's saying, well, okay, he's running some benchmarks and stuff, and he's saying the difference between an addition, which if you implement it really carefully could run in 3 nanoseconds, not 3 microseconds, and the difference between actually touching an SSD is the difference between 3 nanoseconds and 20,000 nanoseconds. So that's a difference of around 10,000x. But the difference between an addition and, say, a storage load is the difference between 3 and back in the day when Ethereum first started, 50. That's 20x at most, right? The difference between 20 and 10,000 is quite substantial. There's a very substantial difference there. So there is some mispricing that happened here. Okay. Now, before I get to the side of demand, we can talk a bit about the motivation for why we're trying to do all this. And the motivation is that we want to scale blockchains. This much is obvious, right? There's L2 Amsterdam, right? We want L2 solutions. We want to scale Ethereum. We want to have a much larger transaction throughput without sacrificing on some of the nice properties that we have out of blockchains. And when you scale any software system, or I guess any system really, you really need to target the bottleneck. If you improve the performance of something that isn't the bottleneck, then the system as a whole isn't going to run any faster. Right? You really need to specifically improve the performance of the bottleneck. So what is the bottleneck for Ethereum and the EVM? Here we have Peter. He's the lead maintainer of Avalanche's C chain. He's saying that I'm going to read the tweet in case anyone's listening from home as a podcast or something and they're not actually looking to the slides, which is Ava people often tout that Ava reached Ethereum's throughput, but that's not the bottleneck. We artificially limit Ethereum to avoid hitting disk limits. These, however, Ava still has 1.5 orders of magnitude to grow until it starts to feel the same problems. So essentially what he's saying is that the bottleneck isn't, as some proponents of alternative chains may claim, it's not consensus. It's something to do with state size, right, and state access. And this is, I guess I'll go to the next slide. Okay, so there's kind of 3 primary bottlenecks. One of them isn't really a bottleneck so much as a parameter, but essentially the first 2 here in red are the hard physical bottlenecks. One of them is state growth, which is that the Ethereum state size continues to grow as you add more, transactions to the chain. You expect that the size of the state continues to grow. And if you're doing everything completely naively, like Ethereum 1, and you don't have any state expiry or any state rent or anything like that, if you just do things completely naively, the state will just continue to grow forever. This is a problem because nodes must keep around the entire state of the system in order to verify new transactions. For those of you who aren't familiar, the state is things like account balances and contract storage. So intuitively, if you receive a new transaction, if you don't know the balance of everyone on the chain, you may not be able to actually verify that that transaction is valid. To be able to be guaranteed 100%, no matter what, that you can verify for sure those new transactions, you must have the entire state of the system. So you can't discard it. This is different than history. And now that blockchains are being designed more and more for a modular world where the separation of data availability and execution, this is going to become more relevant. But history is just the actual transaction data. And after you've actually executed and verified a transaction, you don't really need to keep track of the transaction that created that state. You can actually, as a node, just discard it. And that's history. And there's various proposals for history pruning. I don't remember the exact EIPs, but maybe one of them is related to EIP 4444. But state growth, the state is a problem. State growth is a problem because you cannot discard state. So how big is the state size in Ethereum today? I think last I checked, it's somewhere like 170 to 200 gigabytes, which is quite large, right? Like there's no way you can fit that in RAM. You can't even fit that on some phone storages, right? You can't, I don't know how many phones nowadays have like 256 gigabytes of storage. Very little, right? So you need to put this somewhere. Specifically, you have to put it on an SSD. Why? Because when you verify a transaction, let's say it's a transaction that wants to transfer Ether from one person to another, you are essentially having to do a lookup into the state to make sure that the first person has enough balance, and then actually apply the effects of the transaction, subtracting one person's balance, increasing another. And this is essentially a completely random access into this database. Random access memory, like RAM, exists so that it's fast for random access. Traditional hard drives with a spinning platter are not designed for random access. They're designed for very fast sequential access. So they're basically, you can't use a traditional spinning platter hard drive for state. You can just store it in a high performance SSD, which is very expensive. So you have this huge state, 200 gigabytes, it has to be stored on an expensive SSD. These are issues. And as Ed Felton was saying just a couple hours ago, any layer 2 system that inherits the EVM that is essentially just a fork of Geth, like any other chain, like Avalanche, like Binance Smart Chain or anything, they will all encounter the same issues. If they're running the EVM, they will encounter exactly the same issues of state growth that Ethereum does today. And if they process more transactions per second, they'll just encounter those issues faster. Right? So these are the bottlenecks, not consensus. So an EVM rollup doesn't actually solve these bottlenecks. Right, so it provides scalability in the temporary case at best. In the worst, it's not exactly very good to run it at high throughput. The second hard bottleneck here is disk I/O. So this is as the state grows larger, well, you still have to do random accesses into the state. And SSDs haven't really gotten much faster in terms of like how much I/O they can process randomly. Maybe some of them, maybe every 5 years they double in sequential read and write capacity, maybe. But that's like every 5 years. CPUs double their throughput like every 1 year. So there's no comparison between the two. So you generally don't want to have a system that's bottlenecked by some piece of hardware that improves very, very slowly. You want to ideally be bottlenecked by a piece of hardware that improves very quickly, such as a CPU. Okay, last but not least, this one is more of a political point rather than like a physical point, which is initial block download. This is something that a lot of chains ignore. The Ethereum, like the parameters set for the Ethereum block size aren't just, okay, I can run a node at maximum throughput, I get a new block and all I'm getting is one block at a time, how much TPS can I process? Because Geth on a normal laptop can process on the order of 1,500 transactions per second, not 15. That's like 100x. So really, we want somewhere a factor of around 30 to 100x, that like some sort of a factor that nodes can actually verify transactions and blocks faster than they're produced, so that they can do initial block download and catch up to the tip of the chain from Genesis, right? Because you want to be able to ensure that the entire chain from Genesis is valid. To do that, you need to be able to validate it faster than it's produced. And a lot of other chains kind of ignore this last parameter and they say, well, why don't we just set this parameter to 1? Why don't we just say, okay, you're already at the tip. Now you can just barely keep up. Obviously, that's not good because it means as soon as you fall out of sync or if you're trying to synchronize a new node, you can't actually be sure that the history of the chain is valid. Okay, so those are some bottlenecks. Now let's go on to demand, right? We want to scale blockchains. Let's see how we can use demand to help us. So first, we're going to talk about Bryces Paradox, I'm not sure how to pronounce this guy's name, and Yevon's Paradox, which are both very similar, but it's essentially the observation that if you have a certain amount of traffic and congestion in your roads, if you increase the capacity of your roads, like you double the lanes, let's say, you don't actually decrease traffic like you would expect, and you don't even keep traffic at the same density, but rather you can very often, and most of the cases, it'll actually increase the density of traffic. Like, it's not just like if you double the number of lanes, you have double the number of cars, you'll actually have more than double the number of cars coming in. This can be explained for various reasons, one of them being people are selfish, and if they see this nice road that is the fastest way to get to where they're going in the shortest distance, and it seemingly has a lot of capacity, well, they have more of a tendency to go there, right? And this is why you end up with things like this, right? So there's some game theory and some nuances involved in this that these aren't just mathematical constructions that, okay, I take some number and double it, and then I get some other number doubles. No, there's some nuance there because humans are inherently selfish. So we're going to do a little bit of a case study for gas token and EIP 3529. For those of you not familiar, EIP 3529 was, I think, implemented the same time as the London hard fork, which had the big EIP 1559 that everyone's excited about because it burns ether and number go up and all that. This one was actually, I think, the more interesting of the EIPs that were included in that hard fork. It didn't even eliminate, it just reduced the amount of refund you get for clearing storage. And the story about this is that when the EVM was first implemented, people said, hey, you know what would be really good if we gave people back money, if we refunded them, if they cleared state. Because as we just saw in the previous slides, state growth and state access and stuff is like is the bottleneck, right? So if you refund people when they clear state, I mean, that sounds good. You incentivize them to clear state, right? It turns out that no one actually did that. Instead, what happens is Phil Diane proposed this thing called gas token, which is basically saying, well, why don't I just fill up a bunch of state, and then later on, fill up a bunch of state when gas prices are cheap, mint a bunch of gas tokens, and then later on, when gas prices are expensive, then I'll free it. I'll free those storage slots to essentially make the amount of gas I spend at the more expensive gas price less. So this is a way to essentially hedge gas price volatility, which was a pretty ingenious construct, but it had the unfortunate side effect that now miners and everyone would just start minting a whole bunch of gas tokens and then hoarding them. So now the Ethereum state size just exploded. It went from 20 gigabytes to 100 gigabytes very quickly, and now it's at 200, right? In large part because of gas token. And there was actually interesting things that mining pools would actually do things like mine an empty block with no other transactions, so there would be no transaction fees. They would just mine an empty block that just had a gas token. And they'll just keep the gas token for themselves and not distribute it to their workers, right? Because there's not directly a fee in protocol, like it's not a transaction fee, so the workers, the miners, the people who actually have the hash rate can't really see that, this is actually a gas token, oh, I should get some of this profit, right? So there's a lot of really funky stuff going on with this. And what EIP 3529 did, they said, okay, let's reduce the amount of refund you get. And then overnight, gas token died. Right? So there's like a kind of non-linear effect in this, just like what you have with the Evans paradox, just like what you have here, where like small nudges into the gas pricing of these things or into gas refund schedules and stuff can make a very substantial difference into how people behave. Okay, so we're going to do a thought experiment, which is, let's consider the thought experiment where we double the cost of a storage write or a storage read, right? Do we expect that the usage would exactly halve? Do we expect that it would less than halve? In other words, there would be a sublinear relationship? Or do we expect, much like Evans paradox and much like what we saw with gas token, that there would be a superlinear relationship and that there would be much, then that it would more than halve, that essentially there would be much less usage, and it would be even super linearly proportional to the doubling of this cost. I posit that it'll be the last one, that it'll follow what we've seen with gas token, it'll follow what we've seen with the Evans paradox and stuff. because ultimately these aren't just numbers, hard numbers, and they aren't just mathematics, but rather there's some game theory and some humans involved. Okay, so I'm going to do a little bit of TLDR and how we can actually apply what we've talked about here to blockchains. So traditionally, blockchains, they've determined the gas costs of instructions by benchmarking them, right? You take the computer or whatever, you just run through it and you say, okay, my node can execute this block in this much time, and this is how much time each instruction takes. Therefore, we should adjust the prices of the gas to match that. And every few years, the Ethereum chain undergoes a hard fork that changes the gas schedule. Right? S-load, the storage read went from 50 gas to 200 to, I think it's 2,000 now, something like that for a cold storage read. I don't remember, but like it increases every time, right? Why? Because the actual physical cost of running these instructions does change over time, right? As the state grows larger, you have this big ass state tree, it grows larger and larger. Accesses into the state tree take longer as the state grows. And other things like the gas cost of some instructions, especially cryptographic precompiles, was actually reduced over time because the implementation of those things was improved over time, and therefore we could reduce the gas cost proportionally. Right, so gas cost has changed. And every time they change, you run the benchmark and you say, okay, this is how much I should change them by. And I say this is bad. This is completely wrong. Because demand follows supply superlinearly. Which means, now we get to the topic of this post, you can actually induce demand by manipulating supply for better long-term results. And what this means is rather than going in the direction of, okay, I'm going to benchmark the current implementation and compute gas costs from there, what you actually do is you use the gas costs to make the node implementation behave a certain way and benchmark a certain way. So for instance, if your current bottleneck is storage, if you say, okay, storage is a really big problem, people use storage way too much, right? Storage is underpriced, and a few slides ago we saw that storage was underpriced by several orders of magnitude. Why don't you just make storage really expensive? What's going to happen is, yes, it'll be overpriced compared to how much storage physically costs to use, but it means that you will actually make your blockchain use storage less and move the bottleneck from storage to something else. And it could be CPU. And this is why we want to scale blockchains. We want to move the bottleneck from something that improves slowly, like storage. SSDs really don't improve that much faster every year. We want to move it from storage to CPUs because CPUs improve a lot every year, right? Like just look at the new M1 Mac that everyone's so crazy about, right? It's like insanely fast, insanely low power consumption, right? The CPUs improve very substantially year over year. We want to move the bottleneck to that, and you can't move the bottleneck if all you're doing is reactively setting the gas price. But if you proactively set the gas price to induce demand for block space in a certain direction, then you can make your bottleneck anything you want, such as CPU. Okay, so to find out more about what we're doing, again, I'm one of the co-founders of Fuel Labs, so this talk is brought to you by Fuel. You can visit us at our website, fuel.network. Our GitHub is Fuel Labs, and our Twitter handle is fuellabs_. And I'll kind of give some closing thoughts into why this applies to the work that we're doing, which is that for the Fuel network, we're building the fastest modular execution layer, which is going beyond what a rollup can do, and it's optimizing for a modular world where you have a large amount of data availability capacity, and execution is what is ultimately the bottleneck. So you don't have to optimize for making your transactions very small, but rather you optimize for making your execution as efficient as possible. And for that, you want to avoid the bottlenecks and the pitfalls that the EVM currently has. And how do you do this? Well, you do this by moving the bottleneck to CPU. Because if you have parallel transaction execution, which we do, we're the only execution layer that does, and you make the bottleneck CPU, now suddenly your execution layer can go many orders of magnitude faster than what a classical rollup can do. Okay, so we have like 1 minute left or 30 seconds, so maybe one question or maybe not if our MC complains. Okay, he says no questions. So if you want to find me, if you have any questions after, I'll be around and you can find me. Thank you so much.